Okay, so we're going to be recording this session. If anybody has any objections with the recording, please say so now. So we're still on the topic of steady state error. And so just to remember that when we're talking about steady state error, we're asking the system to do something, either to go to a certain position or a certain fixed reference, a reference that has constant movement or a reference that has constant acceleration. And if the system is stable, in the end, we want to be able to identify how closely the system gets to that goal. And the measure of that is called the error. Now, the errors of systems can be calculated using these expressions based on the forward transfer function. This is important. We're working with the forward transfer function, assuming that we have unity feedback. Okay, we're going to see how we get around this if the system does not have unity feedback, but we're talking about the forward transfer function, unity feedback. If we have that, we can find the steady state errors for each of the typical types of inputs that represent a fixed value, a moving value, or a value with constant movement, or a value that has constant acceleration. And we can find the steady state errors of these. And these are related to three constants that are called the position constant, the velocity constant, and the acceleration constant, which are named or tagged as the steady state error constants. Okay. By the way, further along, we're going to be talking about other constants for the controllers in particular. So we're also going to be talking about Kp, which is the proportional gain. This has nothing to do with that one. The Kp that we're talking about here is the steady state error constant. So we have those. Now, depending on the system is how it's going to react to these. And that's the last thing we were talking about. So systems are going to be classified according to the highest order of the S factor that's multiplying in the denominator. So if we have no S, it's called type 0, I'm sorry, which this is basically S elevated to this power. And depending on the type of system, it's how it's going to react. So a type 0 system, one that doesn't have an S, is going to have a constant error with regards to the step. It's not going to be able, I'm going to take what somebody said last class, it's not going to be able to do its job with regards to moving, references. If the system is type 1, meaning that we've got an S in the denominator, it's going to have a very good response with regards to the step. It's going to have a constant response with regards to the ramp. So it's not going to exactly follow the object, but at least the error isn't going to grow. However, it's not going to be able to do its job with regards to the acceleration. Lastly, if we keep on going, if the system is of type 2, meaning that we have an S squared in the denominator, then it's going to have a 0 constant for the step, 0 error for the velocity, I'm sorry. For the velocity in the step, it's going to be a 0, so it's going to be able to match them or do its job very well. And in the case of the acceleration, it's also going to be able to follow it with a constant error, okay? And so on and so forth. If we were to elevate even more the degree of the S3, S4, we would even eliminate the error for the parabola. And so this is important because actually when we're going to talk about controllers, basically one part of the PID controller is actually adding this S in the denominator somehow. So, and that's the integral component. We talked a little bit about that last session. Mariana asked a question about that, and we talked about that. In the denominator, the S is given, or we can increment the value of S by adding the integral component of a PID. And so any modification to the integral constant is going to improve the steady state error. So this is kind of a summary of this. So it's always important to identify the type of system to be able to relate it to the type of response that we want the system to react to. Now let's look at these three systems here. It's actually, the systems are very similar. And we are asked to find the steady state responses to different situations for unit steps, ramp, and parabola inputs. Okay. So we want to evaluate that. Okay. We're going to evaluate that and see how the systems react. Okay. So let's see what happens there. Let's start with the first one. And we're going to leave these expressions here, which are going to be useful. And we're going to evaluate how the system behaves. Now, this transfer function that we have here can represent really represent any system. Okay, it can represent any type of system. I'm usually referring to the antenna system because it's the one we've kind of understood up to this point, but it could really represent any sort of system. Okay. And so the first thing that I would ask you guys that we need to identify is, can somebody tell me what is the type of this system? What type of system is it, according to what we had just discussed? Can somebody tell me the type? Type 0, type 1, or type 2? Anybody? And remember that the type has to do with the S in the denominator of the forward transfer function. So what type of system is this? Anybody?
Type 2.
Type 2, why?
Because the denominator has 2s.
Well, actually, no. The denominator well, first off, the denominator doesn't have two s's. It's actually a third order system.
Yeah.
Sorry. Okay. So what type would it be? Anybody? Okay, remember what we talked about. The type is defined by the lonely s that's multiplying the denominator. So if I were to put an s here, what is the power of the s that's here in this denominator?
0.
0. It's s to the 0 because we don't have an s. Okay. And so the type of the system in this case, it's a type 0. Actually, remember this in the next whenever we do our next exam or in the final. These are the types of questions I'm going to ask. More than the calculations that can be easily done, I'm going to give you a transfer function. And first off, tell me what type it is. Okay. So, or a system. I'm sorry. I'm going to give you a system. And I'm going to ask you what type it is. It's a type 0. Okay. So if it's a type 0, what would I expect from this system? Would it do its job regarding a step input? Yes or no?
Yes, it would have error, but yes.
Correct. Very well stated, Luis. It is going to do its job, but it's going to have a tiny error, but it's going to try to get to that. Would this type of system be able to do its job regarding a moving reference or an accelerating reference?
No.
No, we've got this little table. If it's type 0, it's not going to be able, it's not going to react well to something that's moving or accelerating. Okay, we would need to modify something here. So good. That's basically what I'm going to be asking in the exam. Literally, that's what I'm going to be asking in the exam. If I have a type 0 system and I give it If I have a type 1 system and I give it a ramp, what would I expect the system? Those are the types of things. Again, it's critical thinking that I want you guys to, the calculations. I mean, come on, you've got MATLAB, you've got a bunch of things there, you can do calculations. Okay, so let's evaluate that. We already know that kind of the answers, but let's evaluate that. So let's look at the first, the step. And let's first evaluate KP. Let's evaluate KP. And so KP is going to be the limit when S tends to 0 of G of S. Okay. And now I'm not gonna, you know, my writing is horrible. I'm not gonna write down the whole, actually I am, just because I need to move my arm and verify that my arm is getting better. I think it is getting better, but I don't want to jinx it, but I think it's getting better, which is good news. I'm so tired this year of going to the doctor. You have no idea. I'm an only child, and they used to take me to the doctor when I was a kid for everything. So I was kind of traumatized about going to doctors since I was a kid. So I didn't like going to doctors when I got older. But now that I'm older, and I've got a family, and I've got a daughter and a wife that need me, then I do go to the doctor because I have to be well for them. But I still don't like going to the doctors. It's been terrible since last year and this year with COVID and arm pain. And I broke one of my molars. My God, how expensive it is to have dental work done. I broke one of my molars, I think in February. Yeah, it must have been February or January, I think. And they still haven't finished working on my molar. It's really annoying. So I really don't like going to the doctor, but I've been having to go a lot to the doctor. That's what happens when you get old. Parts aren't readily available. Yeah, so the arm is getting better. So I've eliminated the limit, okay? So I'm gonna apply the limit directly. So what happens when I apply the limit? Anything that's S is gonna turn to 0. So this is 0, this, and this. This is 0. These 3 are 0. And somebody help me out with the calculations, but I think we can do the calculations ourselves. But the constant for the step would be 500 times 2. It's 1,000 times 5. It's 5,000. Divided by 8 times 10. Well, 10 times 12 is
160.
It's 100. All of it is 160?
Oh, no,
it's
it's a total.
960 is the total.
960.
Yeah.
Perfect. Thank you.
I didn't see the one.
You sure?
Yes.
We don't need to add 1 to that.
Add 1. Oh, good observation. I think it was Marian.
Yep.
We're right now we're doing this, Marian.
Okay.
We're calculating the constant. We haven't calculated the error. So each of the errors has a constant associated to it. So right now we're calculating the constant. We haven't calculated the error. Once we calculate the constant, we have to bring it over here and calculate the error. Okay. So this is 5,000 divided by 960. Can somebody give me that value?
5.2.
5.2, perfect. 5.2, okay. Okay, and so the error, steady state error for the step, meaning what is going to be the difference from, in the case of this system, when it's getting to the value, the error for the step, which is the value going towards infinite, is going to be, now we're going to do that, Mariana, 1 divided by 1 plus KP. And that's because KP is this here. And so this is going to be equal to 1 divided by 1 plus 5.2, which is 1 divided by 1 by 6.2. Can somebody give me that value, please?
0.1612.
0.1612.
1.
1612. Did I write that correct, Mariam?
Yes. Yes, you did.
1612. Okay, perfect. So what does this mean? That the error, I'm going to have a 0.1612. It's a 16%. It's going to be a 16% error, approximately. Okay. Is that acceptable or not? Well, depending on the system, we might need to modify that. But that would be the error I'm going to get for this system. Okay. Questions with this calculation here? The other two are going to be actually very quick.
No. Oh, good.
Okay. So okay, and so this is the error for this step. Now let's see what happens with the ramp and the parabola. I'm going to clear some of this. I'm going to take advantage of this that we have written here, actually. Now, the next couple of calculations are actually going to be very simple. Very simple. Extremely simple. So the next one that we're going to look at is ramp. By the way, we're not doing it right now. I'm not going to be doing it right now, but I suggest as practice, go to, as practice, not necessarily now, but in your free time, since you surely have a lot of free time. It's a joke. I know you don't have free time. Do the test runs in MATLAB. Run this with a ramp, a step, and a parabola, and look at the responses and evaluate the steady state. And you're going to see what we're talking. You're going to see that this is true. So now we're going to talk about the ramp, and the difference with the ramp, or the constant of the ramp, is that we've got that the KV. Actually, this V isn't a very good looking thing. I actually wrote bar there. The KV, which is the one associated to the velocity, is going to be S, the limit of when S tends to be 0 of S multiplied by G of S. Okay, and the only difference here is that we're going to have the transfer function, And the transfer function is going to be multiplied by s. Here. It's going to be exactly the same transfer function, but it's going to be multiplied by s. What's going to happen now when I substitute the limit? So this, and this is going to be 0. This, and this is actually going to be 0. However, by making the s 0, then all of this is going to be 0, actually. Okay. And so if the numerator is 0, the result here is going to be 0. So KV is 0. And over here, so now we've got this here. And we're going to take that over here. If we substitute it in the expression for the error, it's going to be 1 divided by KV. And what happens if I've got a 0 here? 1 divided by 0 is going to be?
Undefined.
Undefined or infinite. And that's what we were talking about. For a ramp, this system is not going to be able to follow something that's moving at a constant speed. It's not going to be able to react with regards to velocity. Okay. Okay. Questions with this one? Okay. Now let's look at the parabola. I'm not going to erase everything, so it's in the video. And now let's look at the parabola. And so in the case of the parabola, which is the input that has to do with acceleration, the constant is going to be called Ka because it's associated to acceleration. And it's going to be the limit of s squared times g of s. So we're going to have an s squared here. So if you notice, it's going to be exactly the same as the previous one. Okay. If you notice here, all of this is going to turn to zeros. So this is going to be totally eliminated. These are also 0. And we're going to get a 0 as a K V. We're going to get 0 as a Ka, I'm sorry. And it's also going to give us a 0 over here in the denominator here. And so the error for the parabola situation is also going to be infinite. So this is not going to do a very good job with acceleration. Okay. Questions with this one? Mariana, please go ahead.
So what's the difference if s is always gonna tend to 0? What's the difference between KV and KA, or the error for the ramp or the parabola?
Oh,
They're gonna get the same answer.
well, those are, we're going to see a couple of other examples where this doesn't happen. So remember that there are 3 things. Mariana, let's try to do this example. Okay. I'm not going to give the example with you guys because you might find it insulting. So I'm going to give the example with myself. let's say that I'm trying to measure how Jorge Sosa reacts to things, okay? Let's see if I'm slow. Let's see if I'm slow or I'm quick, okay? So they're doing a test to me to see if I'm slow or I'm quick or how I react. So they tell me to look forward, and then they put an object in front of me, okay, Marian? You okay up to this point? And they asked me to look at the object. And so I'm turning to look at the object, but I don't actually face the object. I've got a little, so I'm not exactly looking at the object. I'm kind of looking at it, but there's a little margin of distance there, okay? That's my reaction to the step, okay? But now let's say that the object is moving. And they're telling me, Jorge, please look at the object and follow the object while it's moving. And what happens? I'm so slow and stupid that I can't follow the object. The object is moving very quickly and I can't follow it, okay? What's gonna happen? The object is gonna move and I'm gonna be lost in space. That's the reaction to the velocity, okay? So before I go to the acceleration, Marian, I could look at the object and I could position it. But when the object started moving, I couldn't follow it, right? So by logic, if I couldn't follow the object when it was moving, am I going to be able to follow the object when it's accelerating? So said in another way, if I'm so slow and stupid, my Jorge Sosa, I'm talking about myself, not other. If I'm so slow and stupid that I can't follow the object when it's moving constantly, am I going to be able to follow it when it's accelerating? No, right? That's this example here. It's a type 0 system. So the KP is telling us that I can follow the position. The KV is telling me that I'm not going to be able to follow the velocity. And since I can't follow the velocity, I'm not going to be able to follow the acceleration. That's why the logic is constant 0, 0. Okay. But that's
Yeah,
for a type.
now I get why do we need to put an S on the denominator. And
Yeah.
I
Yeah.
know it will change for the ramp and the parabola.
Exactly. Now, right now it's a type 0 system. So we know that a type 0 system is a system that is only going to be able to look at position. We're going to see a couple of other examples that are type 1 and type 2. And so we should see a difference there when we're talking about type 1 and type 2. So basically, if I'm too slow or stupid to be able to follow the objects, they're going to have to give me something to be able to at least follow the object. That's a modification we would need to make. But for this particular situation, right now I'm doing the complete example. However, I'm doing the complete example so you have that documented. However, if I were to tell you it's a type 0 system, you could have automatically not had to do the calculations for KV and KA and the ramp and the prop. You can basically look at the table that I already gave you and say those are going to be infinite. Okay, I'm doing the example just so you have the demonstration, but really by default, by knowing the type of the system, we're going to be able to know which responses are going to be valid. Okay,
Okay.
Is that relatively clear?
Yes.
Okay. So yeah, actually by knowing the type, and let's see if we can. Give me a moment. Let's see if the next examples, based on what the discussion that Mariana and I had right now, let's see if we can do the next examples without having to do all the calculations, just by identifying the type, okay? And we'll do that when we come back from break. Okay, so now let's look at another system. And I think we're going to be able to go more quickly with these, with what I'm going to call the Marian theorem of why the heck are we doing so many calculations that we don't need to do. So we're going to be able to go more quicker with this one because now we understand a little bit better what's happening. So now let's look at another system. It's very similar to the other one. It's got a few other things. Can somebody tell me what type this system is? Mariana, go ahead.
1.
Type 1, correct. Correct, very well. Well done. It is a type 1 system. Why do we know it's a type 1? Because we've got the S here. We've got a lonely S here that's elevated to the power of 1. Okay, so it's type 1. And it's type 1, so let's see the behavior. Now, let's think a bit further. If it's type 1, it means it's not going to have a steady state error for a step, meaning it's going to be precise for a step. So we already know what we're going to get there. It means that it is going to be able to do its job and have some sort of error for the ramp, and it's not going to be able to do its job for the acceleration or the parabola. Okay, let's just validate that. I think, again, we're going to be able to go a little bit quicker. So for the KP, it's going to be, for the step, it's going to be the limit when S tends to be 0 of G of S. And we've got the expression here. And now what's going to happen is that this, and this are 0. And this, and this are all 0. However, the whole denominator is going to turn to 0 because I've got the S here in the denominator. So the whole denominator is going to turn to 0. So if the denominator is equal to 0, this is going to be equal to infinite. And now when I calculate the error, it's going to be 1 divided by 1 plus Kp. 1 plus infinite is a little bit more than infinite, which is still infinite. So 1 plus infinite is still going to be infinite, and 1 divided by infinite is 0. Okay. So once we increase the type of the system, now we have a precise response with regards to steady state to the step input. Yes, Pablo, go ahead. You've got your hand raised, please.
Okay, so I wasn't here last class, so maybe I'm like mistaken. If we have a type 1 system, would it be KP or KV?
Okay. So first off, 1 is the type. Okay. So the type has to do with the S, and we define it as 0, 1, 2, etc. And depending on the type, it's how the system is going to respond in steady state to the step, the ramp, or the parabola. Okay.
Oh, okay.
So depending on the type is how the system is going to respond to each situation. So we already saw in the previous example that for a type 0, it's really just being able, again, to do its job with an error for the step, but it's not working for the
Ramp or parabola.
Mhm.
Okay.
Now we are looking at the type 1, and it's working very well, perfectly for the step. It's doing its job for the ramp, but we're going to see that it's not going to be doing its job for the parabola. And that's what we're basically demonstrating. Okay. Was that clear?
Yeah.
And so this one right now is the one where we're calculating associating.
For the step, I see now like the step, ramp, and parabola. Like I didn't read that. It was too small.
Yeah, those are the three errors that we've got. So for a type 1 system, we don't even have to do the calculations. For a type 1 system, it's going to have a 0 steady state for a step. Okay. Now let's look at the ramp, and we're just going to modify a few things here. I don't know if I'm going to miss this or I miss writing in the whiteboard more. Actually, I like this a little bit. So for the ramp, we're going to have the following. Now for the ramp, we're talking about KV. And that's going to be the limit when of S G of S. That means that I've got an S here in the, that's multiplying the transfer function. Okay. Well, the difference between doing this and doing it in the whiteboard actually is that I don't know if you've noticed that I can automatically generate the notes. So I just take a print screen of this, I include it in the PowerPoint, and it's automatically in the PowerPoint, which is, I find really, really practical actually. This is KV. And so now let's see what happens with the ramp. In the case of the ramp, we're going to have now S multiplied by GS. So what we're going to have here is that we're going to have an S here in the numerator that's actually going to cancel out with the S in the denominator. And what we're going to have here is that this one, and this one, these three are going to be 0. This, and this are also going to be 0. So what we're going to have, somebody help me out with the calculation, it's going to be 500 times 2 times 5 times 6 divided by 8 times 10 times 12. Okay, I just noticed that I think I erased a plus here. Okay. Somebody help me out with the calculations there, please. Okay. I think Pablo, you raised your hand.
I got the result. It would be 31.25.
31.25. Okay, please. Thank you, Pablo. Please validate that just so we know that we're doing the. Somebody else also do the calculation. So just so we have some validation. I'm going to do it also 500 times 2 times 5 times 6 and 8 times 10 times 12. Yep, 31.25. And the error in this case is going to be 31.25, 1 divided by 31.25. What would be the error there?
0.0032.
1, could you say that again, please?
0.032.
0.032. So actually there we've got an error of, we've got an error of about 3% is going to be the deviation we're going to have there, which is it's not that bad. Again, it's doing its job. Okay. This is for the, I didn't write it down. This is for the ramp. Just have that note there. And we're talking about this one here. Okay. So this image, okay. And lastly, let's go to the last one, which is going to be the parabola. And what's going to happen with the parabola? I mean, again, I'm going to do it here just so I'm actually not going to do, I'm not going to write everything again.
We're going to get infinite error.
Correct. Very well. So this, a type 1 system is going to be, let's say, perfect for the position. It's going to do its job for the velocity, but it's not going to be able to work for the acceleration. So in this case, for the parabola, For the parabola, we're going to have a Ka here. It's going to be an S squared. So we're going to have an S squared here. So actually what's going to happen here is that, what's yep. What's going to be eliminated is just the square. So the square is going to be canceled out, but I'm still going to have a 0 here, which is actually going to make all of the denominator, all of the numerator 0, which is going to make this 0. And over here, we're going to have 1 for the parabola. We're going to have 1 divided by Ka. And so this is going to be 1 divided by 0, and this is going to be infinite. Okay, now we're talking about this one. So a type 1 system is going to be okay for the position and velocity. It's not going to be that okay for acceleration. Okay. Let's do a save on this to save here. Okay. That's for a type 1 system. Okay. Questions with this example that we did before we go to the next one? No. Okay. Now let's look at another one last example before we go to a variant here of this. Let me just erase this here. Do some editing. Okay, now let's look at one last example here. This next example, what type of system do we have there? What type of system? It's a type 2 system because we've got an S squared here. Okay, so we've got an S squared. Let me just modify this over here. So now we've got an S squared here in the denominator is 8, 10, and 12. We've added a bunch of other things in the numerator just to kind of make it more complicated. Unnecessary. People who do examples in books, by the way, unnecessary. You can still meet the objective without adding so much stuff. So it's 2, 4, 5. 2, 4, 5, 6, and 7. Yeah, this is just. Bye-bye. S plus 7. My daughter's going to her horsey classes. So we've got that, and we're going to analyze the system, same situation. Now it's a type 2 system. We kind of know of the discussions we've been having, we kind of know what's going to happen here. So if we go to the step first, which is KP, we're going to see the following. Since the limit it is S, the limit of S tends to 0 of G of S, and since we have an S in the denominator, okay, this is going to turn the whole denominator 0, okay, which really doesn't matter what's going to happen with the numerator, since the whole denominator is 0, and just to be congruent with the other examples, these all turn into 0 also. Then what's going to happen, this is going to be equal to 0. Okay, Kp is going to be equal to 0. And since Kp, I'm sorry, not to 0. Kp is going to be equal to infinite. And since Kp is equal to infinite, 1 plus infinite is infinite. This is going to be 0. Okay, so again, a type 2 system, which is this one that we're talking about here, is going to have a, let's say, a perfect reaction to a step. It's going to have a perfect reaction to a step. And we see that there. Save this. Remember, if somebody else has any question, just shoot and raise your hand. Now, if we look at the ramp, we're going to have something very similar. So I'm not going to have to write all of this again. If we've got a ramp now, which is KV. Now it's going to be the limit of when S tends to be 0 of S G of S. So now I'm going to have an S here in the numerator. It's still not really going to matter because this S is going to be eliminated by the square. Okay, but I'm still going to have an S in the denominator, which is going to in turn generate that this KV is going to be equal to infinite. The error, which is the error for the ramp, is going to be equal to 1 divided by KV, which is 1 divided by infinite. So this one, a type 2 system, is going to have a good response to, again, a near perfect response to the velocity. It's going to be able to track the moving object. It's going to be able to track the moving object very well. Okay. Save this. And lastly, just to finish up this example, what's going to happen with the parabola? Well, if I've got a type 2 system, now it's a parabola. For a type 2 system that's going to try to follow something that's accelerating. We'll call this KA. Now the S is going to be an S squared that we're adding here in the numerator. What's going to happen now, these two S squareds are going to cancel each other out. We're going to have these turn into 0. And so are the ones on top. But we're going to have now, somebody help me out with the calculations. It's going to be 500 times 2 times 4 times 5 times 6 times 7 divided by 8 times 10 times 12, which is the 960 that I believe we've already.
875.
875. Okay.
Yes.
Good. Thank you. Thank you, Pablo. So this is going to be KA. Please verify those calculations. Everybody. 875.
He's
Yeah.
fine.
Yeah.
Perfect. Thank you. 875. And so this is going to be KA. And so it's going to be 1 divided by 875. This is going to be a small error. How much?
0.0114.
0.011.
Zero, another zero. That's two zeros.
0011. Something like that. Yeah. So we've got a 0.1 percent of error, which is pretty good. So this means that the system is going to be able to follow the acceleration. So what's the takeaway from this? Well, by adding the s's in the denominator somehow, or adding we can see it this way, because this is actually the way the PID controller works. By adding or incrementing the type of system, or adding an s's in the denominator, we're increasing the type. Adding an S means I'm adding a pole that's located in the origin. Ideally, that's what's called an ideal integrator. So an ideal integral is going to create that. Generating an ideal integral is very, very difficult. So actually what we do is that what we want is a pole that's located in the origin. But if I can have a pole that's very, 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 very close to the origin, we're going to see that it has the same effect. Meaning that I could have an S here to increase the type to type 1, for example. But if I had an S plus 0.00000, I'm sorry, an S plus 0.000001, which is very close to the origin, that would also work, we're going to see. Okay. So this kind of proves what mathematically, or at least or analytically, kind of proves what we were talking about. This one has to do with this one. Okay. Questions with this one before we see another example where we're going to give it a bit of a twist. Okay. I'm going to clear this. I'm going to clear the drawings and move to the next one. Okay, now we've got a variant here. Now we've got a K. And so what is the value of K so that we get a 10% error in steady state? Okay. Now we're using the steady state concept and expressions to try to do the design. Now we've got a K. What would be the value of K if I want a 10% error in steady state? Okay. Well, let's see how we could approach this. First off, I'm going to ask you guys, it's talking about a 10% error. Is the problem giving me the type of input that I'm giving the system? Yes or no?
Yes.
Yeah,
It is?
Yeah.
What type of input am I giving it?
a ramp.
All right.
Well, maybe because you went forward in the slides, but the problem in itself, the problem in itself isn't telling me what type of input I'm giving it. So,
But the RFS wouldn't be the input.
yes, but what type is it? Is it a ramp? Is it a step? Is it a parabola? What type of input am I giving it? Is the problem telling me that right now?
No.
Oh,
It's
no,
not.
no, no.
No, it's not telling me. But however, it's telling me that I want a 10%, I expect a 10% error. So what are we talking about here? Well, let's try to link it with what we were talking about before. Okay, we've got our system here. First thing I'm going to ask is same as last time. What type of system are we talking about in the case of the one we're given? What type of system is it?
1.
Correct, Marian. It's a type 1 system. Okay. It is a type 1 system. And so if it's a type 1 system, we're really talking about this situation here. Okay. We're really talking about these situations here. Okay. Now I ask you, for which of the situations for a type 1 system do I get a constant error? And just look at the table.
With the ramp?
With the ramp. And we're going to, like, it could be arguable if somebody said, well, 0 is a constant. Well, yes, but 0 means I'm exactly there. But if I look at the information I'm given and what we've been talking about, a ramp, a step input is going to give me 0 error. There's no steady state error for a type 1 system. A parabola is going to give me an infinite error. The only situation in which I'm going to have a constant error is the ramp. So actually, the problem isn't telling me the type of input. I could infer the type of input that we're talking about because of the information I'm given. So we're really talking about this situation here. Okay. And so this means that we are actually talking about then this situation here. This is what we're trying to analyze. Okay. So the constant that we're working with is KV. Okay. So I'm going to bring that over here. What color should I use? I'm going to use a different type of color here. So we're talking first off of a ramp. And KV is going to be, I don't know if it's going to fit here. I'll try to write smaller. KV is going to be equal to the limit when S tends to be 0 of S times G of S. And for the expression that we've got here, or rather for the transfer function we're working with, we've got K, which is a parameter we're looking for, times S plus 5 divided by S times S plus 6 S plus 7 S plus 7 and S plus 8. And there's an S multiplying here. Okay. So these are going to be canceled out. And the S's are going to be 0. So this is going to be 0. And this, and this are going to be 0. And that's going to leave me with a KV that's going to be a function of the K that I'm looking for. So KV is going to be equal to 5K divided by 6 times 7 times 8. which is 336. Please verify the calculations, okay? I don't want to make a mistake. 5K divided by 336. Okay. Yep, 6 times 7. Okay. And so we need to relate this to the 10% error that we're talking about. So let's see if I got another slide. We want to relate that to the 10% error that we're talking about. Okay. So this expression that we've got here. Can I, so what I'm going to do is the, what can I do here? This expression that we've got on this side for the ramp, I'm going to try to make the better use of the space here. So this expression is going to be equal to 1 divided by KV. And how much should that error be, according to what we're being told? It should be 10%. Okay. So in this case, the error should be 0.1. Okay. So that means, let me rewrite this over here, make it a little bit smaller. We've got that KV. Equals 5K. Divided by 336. Okay. So from this expression that we have here, we know that we can take that expression and substitute it, and I'm gonna draw it here on the bottom. I'm gonna draw it in green. 1 divided by KV, which is 1 divided by 5K divided by 336. Yep, is equal to 0.1. Okay. Or in other words, if it's 1 divided by 5K by 336, this means that using the old tortilla law, this means that this is 336 divided by 5K. This means that K would then be equal to, I'm actually going to write this down over here. It's still in the video explanation. So this would mean that 336 divided by 5K is equal to 0.1. Okay. And we bring this over here. And this would mean that K is equal to 336 divided by 0.5.
We got 672.
672?
Yes.
Perfect. I'm actually just going to put the final calculation here. So K equals 5.72. $5.72?
No, 600.
672, I think she meant.
672, right?
Yeah.
Yeah.
Okay. Six. Yeah, it didn't make sense. 672. So this would mean that for this system, and if I wanted an error of 0.1 in the velocity factor, or with regards to a ramp input, and I wanted a 10% error for that, then the K would have to be 672. Okay, so now we've used, now up to this point, we've used the stability criterion like the Ruth Hurwitz to be able to do design, find values of K based on stability. Now we can also find values of K based on steady state, which is another thing that we can do. Okay, questions with this one? Or we kind of wrap this up. No? Okay.